Welcome to Satoshi and Solana, the show where we break down blockchain and crypto concepts in a fun, easy-to-understand way.
Today, we are really getting our hands dirty with the Solana Whitepaper. We're going to try and understand not just what it is, but how it goes after one of the oldest problems in all of decentralized systems.
And that problem, really, when you boil it all down, it's just time. It's always about time. So for this deep dive, we're looking at how Solana decided to solve this fundamental issue of, how do you agree on the order of events when nobody trusts anybody else's watch?
That's the entire dilemma right there. I mean, think about most blockchains, what we'd call fault-tolerant replicated state machines. They don't have a central clock they can trust.
Yeah.
So every single node is just running on its own local time. And that creates the big question, how do you get them all to agree that, say, transaction A definitely happened before transaction B?
And usually the answer is just a ton of messaging. It's a huge amount of overhead.
Yeah.
You have node A yelling, hey, I saw this at 10.00.01, and node B is like, well, my clock said 10.00.03. It's that constant back and forth that creates the bottleneck we see in, the older chains.
Exactly. So if you can just get rid of that need to talk about it, if you can prove the order without all that chatter, you basically eliminate the bottleneck. And that right there is the core idea behind Solana's big innovation, proof of history, POH.
So proof of history, this is meant to be the one single verifiable timeline. It sort of encodes this trustless proof of time passing directly into the ledger itself. It doesn't totally replace consensus, but it's combined with proof of stake to get those legendary speeds. So let's really break down POH. If it's this trustless clock, how? How does it actually work? It's not just like reading a computer's clock somewhere, is it?
No, absolutely not. That would defeat the whole purpose. POH is actually a sequence of computation. It's a process that's guaranteed to have taken a certain amount of real physical time to create. And it uses a cryptographically secure function, something like SHA-256, in a continuous loop.
And the real genius is that input-output loop, isn't it?
Precisely. The output of one hash calculation is immediately fed back in as the input for the very next one. It's a loop that has to be run one step at a time, sequentially, on a single processor core.
Right.
And because it's a cryptographic hash, you can't just guess the 100th output. You actually have to compute all 99 steps that came before it. There's just no shortcut. It's unavoidable.
So the resource you're proving you spent isn't electricity, like in proof of work. It's actually time. You're proving time passed because you were busy doing the work, running the hashes.
That's it exactly. So imagine a node generates, say, hash 1, and then a little while later, it generates hash 300. The network doesn't need to look at that node's timestamp. It can just verify that, yep, 299 hashes were generated one after the other.
And since we know how long that takes.
Right. We know how long that computation takes, so it's cryptographic proof that real time elapsed between hash 1 and hash 300. It's like turning computation into a verifiable stopwatch.
That is just brilliant. Okay, so how do you get actual transactions, user data stamped onto this timeline? You can't just wait for the whole sequence to finish.
No, you don't have to. When a transaction arrives, its data, or more likely a hash of its data, is just appended into the state of the function while it's running. The very next hash that gets generated after that data is mixed in, that hash becomes the transaction's guaranteed verifiable timestamp.
So if my transaction gets mixed in at step 500, we know for a fact that it existed before hash 501 was created.
Correct. And just like that, you solve one of the biggest headaches in distributed ledgers, which is somebody maliciously reordering events.
That makes a ton of sense. But what stops the person generating the history, the leader, from just, sticking my transaction wherever they want later on, like hiding it in an earlier part of the sequence to cheat the system?
So there's a really clever defense for that, and it's on the client side. When you create your transaction, you actually include the last valid hash you saw from the official sequence. You bake it right into your transaction data.
Oh, interesting. So you're tying it to a specific moment.
You're tying it to a specific tick of that cryptographic clock. So if a malicious generator tries to publish a different history where your transaction shows up out of order or referencing a hash that never really existed, it's immediately obvious to the whole network. The inconsistency stands out, and they just reject it.
Okay, now that we've got POH down, let's look at the network architecture that lets this thing fly. It's all built around this leader and verifier model.
That's right. So at any given time, the network elects one node to be the leader, and this leader is the only one generating the POH sequence for that period. And their job is huge. They're taking in all the user transactions, sequencing them, executing them, and then publishing the results.
I thought it was fascinating that the white paper says the leader actually orders transactions based on, like, memory access patterns. That sounds more like an operating system than a blockchain.
It's all about raw engineering efficiency. By ordering things to optimize how the computer's RAM is accessed, they just squeeze out the maximum number of calculations per second. The leader does everything in memory, then publishes the final transactions and a signature of the new ledger state.
And then come the verifiers,
Yeah.
the checks and balances, the voters.
Yep. The verifiers are just grabbing that history from the leader, re-executing all the same transactions to make sure the leader was honest, and then they publish their own signatures of the state. Those signatures are basically their votes for the consensus algorithm. It's them saying, yes, we saw this, we agree with this history.
So let's talk about the speed. The white paper does this calculation based on a 1 gigabit per second network. What's the kind of ceiling they came up with?
Well, the theoretical max, which is limited by that network bandwidth, it lands at about 710,000 transactions per second, or TPS. It's worth pointing out that the raw computational limit is actually way higher, like 2.75 million TPS, but you just can't push that much data through a standard network cable fast enough. So 710K is the realistic number.
That's a staggering number.
Yeah.
But it brings up a question. If the leader is running this long sequential POH generation on one core, how can the rest of the network, the verifiers, possibly keep up? Doesn't that sequential process bottleneck the verification too?
And this is where the engineering is just so smart. The generation of the history has to be sequential. That's the whole point. You're proving time passed.
Right.
But the verification of that finished history, that is massively parallelizable.
So the leader might spend, say, 10 seconds creating a million hashes one by one, but the verifiers can check that it was all done correctly almost instantly.
Exactly. Think of it like a movie. The generator has to record the movie frame by frame, sequentially. It takes 10 minutes. That's the generation. But to verify it, you can take that whole reel of film, cut it into 1,000 pieces, and give each piece to a different person to check at the same time. Verifiers do the same thing with GPUs or multi-core CPUs. They slice the POH sequence into chunks and check them all in parallel. They can verify the entire history in a tiny fraction of the time it took the leader to create it. And that's what keeps the whole network moving so fast.
Okay, so POH gives you the order and speed, but the actual security is still coming from proof of stake. What are the basics of their POS layer?
It's the standard model, really. It uses economic incentives. Validators have to put up collateral a bond, and if they misbehave, they risk getting slashed, which means they lose their staked coins. That's the stick that stops them from, say, voting on two different conflicting histories at once.
The old nothing at stake problem. Slashing makes it really expensive to be dishonest.
Exactly. And for the network to finalize a piece of history, it needs a 2/3 supermajority of all the staked coins to vote for it. So the economic cost to launch a successful attack, to try and get a fraudulent history accepted, is enormous. It's at least 1/3 of the entire bonded market cap.
The white paper also gets into the CAP theorem, that classic trade-off between consistency, availability, and partition tolerance. What happens if the network splits in two?
Well, Solana's approach is to prioritize consistency first under normal conditions. It'll wait for, human reasonable timeouts to resolve things. But if a really serious long-term network partition happens, it has a mechanism to eventually switch and choose availability.
How does it do that without, breaking the network? How does it move on?
It's tied directly back to POH, to that verifiable passage of time. If a big group of verifiers suddenly disappears, they get slowly, very slowly unstaked over time. And that process requires a huge number of new POH hashes to be generated. A lot of verifiable time has to pass.
But you can't just kick them out immediately. A bad actor could try to force that to happen.
Precisely. By tying the unstaking to the POH clock, the largest surviving part of the network is guaranteed that if they just keep working, keep generating history, they will eventually shed those missing votes, they'll get back to their 2/3 supermajority, and the network can start processing transactions again. It ensures the chain doesn't just halt forever.
And what about proof of replication POREP? Where does that fit in?
So POREP isn't really for consensus, it's more for accounting. It's a way to make nodes prove they're actually storing the historical data they claim to be storing. When you combine that with POH, you get a defense against forgery that covers both time, the ordering, and storage.
Okay, let's switch gears to smart contracts. The execution engine uses something called eBPF bytecode. What's the significance of that choice?
eBPF is known for being incredibly fast and secure. It usually lives in high-performance networking code. But the key here is that it allows for just-in-time compilation, which is just critical when you're trying to execute millions of small programs without grinding the whole system to a halt.
But the real secret sauce for speed seems to be how they use the GPU, this zero-cost foreign function interface. It sounds super technical, but it seems to be the key.
It absolutely is. So a smart contract often needs to do something complex, like check a cryptographic signature and ECDSA verification. Now, if you have 1,000 contracts that each need to do that, you could check them one by one.
And create a huge sequential bottleneck.
A massive bottleneck. So instead of doing that, Solana's runtime pauses the contracts for a moment, gathers up all those pending signature checks from maybe thousands of different programs, and bundles them into one giant batch.
And then throws that batch at the GPU.
Exactly. It ships that whole batch of identical tasks off to the GPU to be processed all at once, in parallel. A modern GPU can chew through thousands of those tasks in the time it would take a CPU to do just a few. The white paper says you can get a throughput increase of thousands of times doing this. It's how you get high transaction volume in complex smart contracts.
And just quickly, on scaling the generator itself, if POH has to be sequential, how do you scale it horizontally without breaking the network up into shards?
They do it by having multiple POH generators running and synchronizing with each other. Instead of sharding the state, the different generators constantly mix their own sequences state into the sequences of the others. It creates this kind of interwoven, unified timeline. It lets the network track way more events at once without losing that provable global order.
So when you take a step back and look at the whole system, what's the one big takeaway here?
I think the unifying insight really is that Solana's entire architecture is built on successfully turning time itself into a shared, verifiable resource. And they do that with proof of history. By doing that, they remove the single biggest bottleneck that all asynchronous systems face, which is that constant need for nodes to talk to each other just to agree on the order of events.
It's like the difference between a room full of people shouting out what time their watch says versus everyone just looking at a single giant tamper-proof stopwatch on the wall that determines the timeline for everybody.
That's a great way to put it. Because they have that single agreed-upon record of history, the network can be unlocked to hit those speeds, pushing 710,000 transactions per second. It turns this slow, asynchronous problem into a machine that can actually compete with, like, global financial systems. The real power isn't just the speed, it's that the speed itself is trustless.
Thanks for listening to Satoshi and Solana, your guide to making sense of crypto, one episode at a time. Subscribe for more insights and stories from the world of blockchain.